In 1687, Isaac Newton posed a thought experiment that changed how we understand the universe. Imagine a cannon at the top of a very tall mountain, he said. Fire a cannonball horizontally. It travels forward and falls to the ground. Fire it faster, and it travels farther before landing. Fire it faster still, and the earth curves away beneath it at the same rate it falls. The cannonball never lands, it orbits. The satellite and the falling apple are the same phenomenon, separated only by horizontal speed. This insight that horizontal and vertical motion are completely independent is the foundation of two-dimensional kinematics. Once you understand it deeply, every problem involving motion in a plane becomes a pair of one-dimensional problems running in parallel. Today, we formalize this idea and apply it to projectile motion, circular motion, and relative velocity between reference frames. Last week we worked entirely in one dimension. Objects moved along a single line, and position, velocity, and acceleration were scalars, numbers with a sign. Now we step into a plane. Position, velocity, and acceleration become two-dimensional vectors, each with both a magnitude and a direction. The position vector r points from the origin to the object's current location. In component form, r equals x times the unit vector in the x direction plus y times the unit vector in the y direction. The components x and y are simply coordinates, the horizontal and vertical distances from the origin. Velocity is the time derivative of position. V equals dr over dt. In component form, the x component of velocity equals dx over dt, and the y component equals dy over dt. Each component evolves according to its own one-dimensional kinematics, completely independently of the other. Acceleration is the time derivative of velocity. A equals dv over dt, with x and y components each evolving independently. The key principle, stated precisely, the motion in the x direction and the motion in the y direction are mathematically independent of each other. What happens horizontally has no effect on what happens vertically, and vice versa. This is not an approximation, it is exact. This independence is the reason we can solve two-dimensional problems by running two one-dimensional analyses side by side, linking them only through the shared time variable. Time is the bridge between the two directions. Find the time of flight from one axis, then use it in the other. Projectile motion is the most important application of two-dimensional kinematics, and arguably the most important single topic in the first half of this course. An object is launched with initial speed v0 at angle theta above the horizontal. We neglect air resistance throughout. The first step is always to decompose the initial velocity into its components. Horizontal component v0 x equals v0 times cosine theta. Vertical component v0 equals v0 times sine theta. Now we apply the one-dimensional kinematic equations independently to each direction. In the horizontal direction there is no force and therefore no acceleration. The horizontal velocity is constant for the entire flight. V minus x equals v naught times cosine theta at every moment. The horizontal displacement grows linearly. X equals v naught times cosine theta times t. In the vertical direction, gravity acts downward. Taking upward as positive, the vertical acceleration is negative g. The vertical velocity changes continuously. Vy equals v naught times sine theta minus g times et. The vertical displacement y equals v naught times sine theta times t minus 1/2 g times t squared. From these four equations, every result about projectile motion follows by algebra. Time of flight. The projectile returns to its launch height when I returns to 0. Setting y psi equal to 0, 0 equals t times the quantity v naught sine theta minus 1/2 gt. Two solutions, t equals 0, the launch moment, and t equals 2 v naught sine theta divided by g. The second solution is the time of flight. Notice, time of flight depends only on the vertical component of the initial velocity, not the horizontal. Maximum height, at the peak of the trajectory, the vertical velocity equals 0. Setting Vy to 0, t peak equals v naught sin theta divided by g. This is exactly half the total flight time. The trajectory is symmetric about the peak. Substituting back, h equals v naught squared times sine squared theta divided by 2g. Horizontal range, substitute the total time of flight into the x equation. R equals v naught cosine theta times 2 v naught sine theta divided by g. Using the trigonometric identity, 2 sine theta cosine theta equals sine of 2 theta. R equals v naught squared times sine of 2 theta divided by g. This range formula contains a beautiful geometric result. Range is maximized when sine of 2 theta is at its maximum, which is 1 occurring when 2 theta equals 90 degrees, meaning theta equals 45 degrees. The optimal launch angle on level ground is exactly 45 degrees. Furthermore, any two launch angles that add to 90 degrees produce the same range. A 30-degree launch and a 60-degree launch land at exactly the same distance, though they follow different paths. The 30-degree trajectory is lower and faster. The 60-degree trajectory is higher and slower. Same endpoint. The shape of the trajectory is a parabola, not assumed, but derived. From the parametric equations x equals v naught cosine theta times t and y as a quadratic in t, eliminating t gives y as a quadratic function of x. The shape is parabolic regardless of the initial speed or angle. An important conceptual check. A ball rolled off a table horizontally and a ball dropped straight down from the same height land at the same time. Both have identical vertical acceleration. The horizontal motion of the first ball has no effect on the vertical component. This counterintuitive result is verified by experiment and is a direct demonstration of the independence of horizontal and vertical motion. An object can move at constant speed and yet be continuously accelerating. This is one of the most conceptually important statements in introductory physics, and it follows directly from the vector nature of velocity. Consider an object moving in a circle of radius r at constant speed. Its speed, the magnitude of velocity, does not change. But its velocity, the direction of motion, is changing continuously. At every point on the circle, the velocity direction is tangent to the circle, and that tangent direction rotates as the object moves. A changing velocity means there is acceleration, even though the speed is constant. To find this acceleration, examine the change in velocity over a short time interval. The velocity vector rotates, and the change in velocity, delta v, points inward, toward the center of the circle. In the limit as the time interval shrinks, the centripetal acceleration has magnitude AC equals v squared over r. The direction of centripetal acceleration is always toward the center, always perpendicular to the velocity. Because it is perpendicular to the velocity, it cannot do work and cannot change the speed, only the direction. This is precisely why the speed stays constant, while the direction continuously changes. Expressing in terms of angular velocity omega, since v equals r omega, we get a minus c equals r omega squared. The period t is the time for one complete revolution. Since the distance is 2 pi r, v equals 2 pi r divided by t, and AC equals 4 pi squared r divided by t squared. Practical consequence: at higher speed on a curve of fixed radius, centripetal acceleration grows as v squared. Doubling speed requires 4 times the centripetal force. This is why tight curves at high speed are dangerous. The required force grows rapidly and can exceed what friction or structural limits can provide. Next week we will ask, what force provides this centripetal acceleration in real situations? On a flat road, friction. On a banked curve, normal force. Inside a loop, normal force plus gravity. Each situation requires identifying the physical force playing the centripetal role. Physics depends on the observer. The same event can look completely different from 2 different reference frames, coordinate systems attached to different observers. If you sit in a train moving at constant velocity, objects outside appear to move backward past the window. A person on the platform sees those objects as stationary. Both descriptions are correct. They describe the same physical reality from 2 different perspectives. The velocity addition formula connects the 2 perspectives. Suppose frame B moves with velocity v minus BA relative to frame A. An object moves with velocity v object B relative to frame B. The velocity of the object as seen from frame A is v object A equals v object B plus v B A. This is vector addition. Direction matters. In 2 dimensions, both velocities must be decomposed into components and the components added independently. The swimmer and river example illustrates this clearly. A swimmer can move at speed vs relative to the water, say 2 meters per second. The river current flows at Vr perpendicular to the swimmer's target direction, say 1 meter per second to the right. If the swimmer aims straight across, the river carries them to the right while they cross. Their actual velocity relative to the ground is the vector sum of their swimming velocity and the current. The actual speed over ground, the square root of v minus s squared plus v minus r squared equals the square root of 4 plus 1, approximately 2.24 meters per second. The actual direction is not straight across, it is angled downstream. They land to the right of their target. If the swimmer wants to land directly opposite, they must angle their swimming direction upstream, offsetting the current. The angle upstream, cosine alpha equals v minus r divided by v minus s, where alpha is the angle from the straight across direction. For these numbers, alpha equals the arc cosine of 1/2 equals 60 degrees. The swimmer aims 60 degrees upstream. Their path across the river is straight, but their speed over ground is only 1.73 meters per second slower because they waste some swimming velocity fighting the current. This trade-off, straight path versus faster crossing, appears in navigation problems, aircraft flying in wind, and ships sailing with current. The same velocity addition principle governs all of them. In 3 dimensions, the same formula applies. Just extend to 3 components. 2 common errors in projectile motion problems deserve explicit attention. First, using the total initial speed instead of a component. If a ball is launched at 20 meters per second at 60 degrees, its horizontal component is 20 cosine. 60 equals 10 meters per second, and its vertical component is 20 sine 60 equals 17.3 meters per second. Using 20 meters per second in a horizontal calculation, as many students do, is incorrect and gives a larger range than the actual one. Always decompose first. Never use the total speed in a single-axis equation. Second, sign errors in the vertical direction. Taking upward as positive is standard. Then the initial vertical velocity is positive for any upward launch, and the acceleration is negative g, meaning negative 9.8 or negative 10 meters per second squared. The moment you write A equals positive 10 in a problem with upward positive convention, every subsequent calculation is wrong. Establish the convention explicitly at the start of every problem. Write it down, then apply it consistently throughout. A richer version of the range problem, projectile launched from the top of a cliff of height h to the ground below. The time of flight is no longer 2 v0 sine theta over g because the projectile lands at a different height than it launched. The vertical displacement is negative h. It ends below the launch height. Set y equals negative h in the vertical equation. Negative h equals v0 sine theta times t minus 1/2 gt squared. Solve this quadratic in t to find the time of flight. Then substitute into x equals v0 cosine theta times t for the horizontal range. The range from a cliff is always greater than the range on flat ground, because the longer flight time allows more horizontal travel. We have now extended the kinematic framework into 2 and 3 dimensions. The core principle: each coordinate direction is independent. Decompose all vectors into components. Solve each direction separately using the one-dimensional kinematic equations from last week. Link the two solutions through the shared time variable. For projectile motion, horizontal means constant velocity, vertical means free fall. The trajectory is a parabola. The range formula r equals v0 squared sine 2 theta over g. Maximum range at 45 degrees. Equal angles summing to 90 degrees give equal ranges. For circular motion, constant speed does not mean zero acceleration. Centripetal acceleration equals v squared over r, always pointing toward the center. It changes direction, but not speed. For relative motion, velocities between reference frames add as vectors. The observed velocity of an object depends on the reference frame of the observer. Next week we ask the deeper question that kinematics cannot answer. Motion has been described completely, but what causes it to change? That is Newton and 3 laws that explain everything from falling apples to the orbit of the moon.